You do not always need embeddings to get strong results. We will compare TF-IDF to a simple mock embedding setup, so you know when simple is enough. If you feel search or classification is noisy, or your models chase semantics you do not need, this video helps. You will learn when plain text features find the right results, when to add tiny upgrades, and when full embeddings actually justify their cost. No heavy theory, just Python instincts you can use today. I'm Professor Pi, teaching AI foundations from basics to advanced, with simple concepts-first Python that helps you solve bigger, real-world problems. Start with the problem most teams hit. You have short documents, user queries, and a need to pick the best match quickly. People reach for embeddings because they promise semantics. But embeddings add compute, storage, and tuning. TF-IDF and small lexical tricks often hit the sweet spot for small to medium corpora and low latency needs. Intuitively, TF-IDF boasts words that are rare across the corpus. Bag of words counts overlap. Embeddings try to represent meaning in a vector. For short texts, rarity plus a little normalization often gives as good or better practical results than a heavyweight encoder. We will build a tiny retrieval flow. First, a baseline literal match, then TF-IDF weighting, then a top 2 selector, a lightweight synonym fix, and finally a mock embedding average so you can see the difference with semantics. Each step stays on the same tiny corpus, so comparisons are honest. Now a bare baseline for literal matching. This snippet ranks a tiny corpus using plain bag of words overlap. The dictionary docs holds short documents keyed by simple IDs, and the string Q is our query. The function toke lowercases and splits text into tokens for simple matching. We compute the overlap size between the query tokens and each document's tokens, then sort by the count and break ties by the ID. Finally, we print the highest scoring document ID as bow top. The printed ID shows which document shares the most literal words with the query, highlighting the baseline behavior of exact matching. Next, upgrade the scorer to weight rarer words more. This snippet upgrades the scorer to TF-IDF using Python's math log. We build DF to count in how many documents each token appears, then compute IDF with add1 smoothing, so unseen or ubiquitous terms behave safely. For each document, we sum IDF weights of tokens that overlap with the query, which boosts rarer words and downweights common ones. We sort by this weighted score and return the top document as TF-IDF top. Increasing the smoothing to +1s reduces IDF extremes, while decreasing it amplifies rare term influence. The printed ID reveals how rarity-aware weighting can shift emphasis compared to raw overlaps. Now look at a small candidate set instead of a single winner. This snippet selects the top 2 documents by TF-IDF to compare ranking. It reuses the IDF dictionary and the toke function, computing an IDF-weighted overlap score for each doc in SC. We sort scores descending and take the first 2 IDs, storing them in top 2 for a quick, visible ranking slice. Returning 2 results reveals whether relevant options cluster near the top or if one document dominates. The printed list shows the best small set to review, which is often what you need for retrieval-driven features like previews or candidate generation. Next, add a simple normalization to reduce brittle misses. This snippet applies a tiny synonym map to expand matches pragmatically. The dictionary synd rewrites specific tokens to a shared form, and the function norm applies that mapping to token lists. We measure literal overlap between the query Q and document A, then repeat after normalization to see how many extra hits appear. This kind of lightweight normalization brings near synonyms together without heavy models. The printed overlap gain quantifies the improvement, showing how a simple tweak can recover missed matches and reduce brittle literal dependence. Finally, show how a basic embedding average behaves when semantics matter. This snippet uses a mock embedding average to score semantic similarity. The dictionary vex assigns tiny 2D vectors, so food words share one axis and instruction words share the other. The function E averages token vectors for any text, ignoring terms not in vex, so unknowns don't distort the mean. We scored each doc by the dot product with the query Q2, which captures alignment across both axes, even with no exact term overlap. Adding more synonyms or dimensions can sharpen discrimination at the cost of more computation. The printed embed top shows which document is semantically closest when literal matches fail. Across these 5 steps, you see a clear progression. The bag of words baseline finds exact matches quickly. TF-IDF prefers distinctive words and often corrects common word bias. Returning a top 2 helps user interfaces and candidate pipelines. A tiny synonym map fixes brittle misses with almost no cost. A mock embedding shows how semantic alignment can recover relevance when words do not overlap, what it is, when to use it, and one caveat. TF-IDF is a rarity-weighted lexical scorer that is fast and explainable. Use it when your texts are short, your corpus is hundreds to thousands of documents, and latency matters. Caveat: TF-IDF cannot recover deep semantic differences and will fail when synonyms and paraphrases dominate. Next step: tune the TF-IDF n-grams and the IDF smoothing to see how that shifts precision and recall on your actual corpus. Try adding a small approximate nearest neighbor index if you grow past a few thousand items. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.